What happens if the data are not normal? So let us say we encounter a data which is non-normal. So first thing you have to see is whether the data are continuous or attribute. If it is continuous, then I'll take some action. If it is attribute, I have to see whether the data are defective or defects. Defectives or defects. And both of them will not be normally distributed. Defectives are having another distribution called binomial distribution. Defects have another distribution called Poisson distribution. So in this case, we have to treat them differently. Let me first talk about binomial. So binomial means, suppose my quality is at, I say that if I collect sample 100 or say some samples size of 100, I'm likely to get how many defectives? Approximately 2 defectives. If I go on collecting 100 samples, so even though the population is 2% defective, it's not that every time I will get, like, this is the population, let us say, which is containing 2% defectives. But if I collect 100 samples from this population, I'm not going to get every time 2. Sometimes I will get maybe 1 also. Sometimes I may get 0 also, sometimes. But most of the time I'll get 2, sometimes 3, even 4 also, 3, and so on and so forth. So if I take, this is 100 samples every time, I can even take a different sample size, then I'll have to calculate the proportion defectives. So I want to avoid that. That is why I'm taking the same sample size. Now, if I plot the data, histogram will look something like this. The maximum it is 2, sometimes it is 1, sometimes it is 0, and then I've got something like this. Very rarely I will get 6. There is a likelihood of getting 6 also. Okay, so that follows some other distribution. Now I have made this distribution, but doesn't mean that the shape of the binomial distribution is like this. No, it keeps changing with proportion of defect. Suppose you are having 50% defectives in your process, suppose. So your process will look something like this. It will look like a normal distribution. Suppose here it was like 0, 1, 2. Suppose it is 50% defectives. So most of the time you get 50, right? And that it will be like a normal distribution. So the binomial distribution doesn't have a specific shape. It depends on the proportion defective. Similarly, same thing with Poisson distribution. Poisson distribution is like here, n is 100, defective is 2. Here in n is like very large number, like number of complaints, defects. Generally, defects have got a lot of opportunities, isn't it? So number of complaints, I am receiving 5 complaints every day. Out of how many? Maybe 1,000 customers. Sometimes 2,000 customers, maybe. I don't know. When it is a larger number, so such distributions will follow Poisson distribution, some other distribution. Okay. And the standard deviation also differs. The standard deviation for binomial distribution is P into 1 minus P. P into 1 minus P. Okay, this is P into 1 minus P. And the other one The standard deviation for Poisson distribution is square root of C, where C is average number of defects. And here P is proportion, average proportion of defectives. So in this case, if in my example here, P is 2. So the standard deviation of this will be 2 into 1 minus, proportion. Proportion will be 0.02 multiplied by 0.98. 1 minus 0.02. Proportion, right? 2% means proportion. Minitab uses all those formulae to calculate the standard deviation. So when we did, if you remember, when we did our P chart and NP chart for binomial for defectives, we did a P chart. So Minitab was calculating the standard deviation using this formula. When we did our C chart, defects, for defects we did C chart and U chart. So Minitab was calculating using this formula. So Minitab will do all its job using the right formula. Only thing is we have to just choose the right control charts. Now coming back to our continuous data. So in case your data is continuous, then in that case, first check for outliers. And if it is like check outliers are there, yes, so now it becomes normal. Suppose outliers are not there and still it remains non-normal, then check for segmentation. Segment the data or stratify the data. The different segments or different stratification groups. We call it as groups, right? Groups. Make groups. Okay. So you can make groups. And maybe after proper groups, it will become normal. If yes, then it becomes normal. And still it is non-normal. So then there is something called Box-Cox transformation. Now it is an overkill, but it is there. So either you transform it, but I suggest that in case it is a no, my suggestion is treat it as non-parametric. Because non-parametric, if you do Box-Cox transformation, it's like you transform the whole data, try to fit in like one whole data divided by 1 divided by that x, or try to make it e raised to the power of minus x, where x can be any value. So this is like I'm trying somehow to fit the whole thing into normal distribution. Not why. I can consider, I can do a median test. But in Master Black Belt, actually, I teach that Box-Cox transformation also. So if it is still not possible, then of course you use non-parametric tests. Okay. So this is the roadmap of how to deal with the non-normal data. So the data are not normal, you can use this. Okay. So that was about dealing with non-normal data. So till now we have seen the continuous and attribute data. And when I have got continuous and attribute data, I will be using 2T or ANOVA or Mann-Whitney and mood median and the respective tools which I just saw. Now, what happens with attribute and attribute? So attribute and attribute is something like, let's say, errors, mistakes, defects. Okay. So let us take an example. There are two nurses, nurse A and nurse B, in a vaccination center for COVID-19. Nurse A is, let's say, every week, when both of them are giving vaccination to the patients, not all the people who are coming for vaccination. Nurse A, number of times people complain after getting vaccinated. It's like 10 complaints we receive for nurse A, that the people got some pain after the vaccination. And for nurse B, we receive 20 complaints or 20 pain issues, like pain related issues. So which nurse is better? Which nurse is better? Now, most of the people will say A, but now you are a black belt, you should not say like that. Errors, mistakes, pain, all these things are attribute data. So whenever you are dealing with attribute data, you have to ask for for that another category. So here it's like pain or complaints. If I say complaints, if I want to make it as complaint, complaints 10 and 20. The other category would be non-complaints. Or if I want to make it a little easier for my calculation, let's say total. So non-complaints are 90 for A, complaints are 10, non-complaints are 90. So total is 100. For B, let's say total is 200. Now tell me, is there any difference between the quality here, or errors or complaints, or proportion of complaints here? Now there's no difference. A and B both are same. Whenever you are dealing with attribute data, you'll be talking about categories. And then you'll be creating the frequency. So here, let's say mistakes, and here I was trying to establish whether the nurses, is there any relationship between the nurses and the mistakes? Means some nurses committing more mistakes as compared to other. So I've got two nurses here, and I'll create a frequency table. We call this as a frequency table. Just now I created a frequency table. So here there were two proportions, so I'll do two p-tests. Okay. I can also do chi-square test. Okay. So if I were to do two p-test, nurse A and nurse B, 10 and 10 upon 100, 20 upon 100. If I do two p-tests, let us say, null hypothesis is both nurses are same. Null hypothesis is both nurses are same, means there is no difference between, or there is no relationship between nurses and complaints. Means nurses are not the root cause. Nurses are not root cause. Nurses are the root cause. Nurses are. See, in every case, every patient case, like nurse A, B, C, everyone 10% of the patients are complaining about pain. That means problem is not in the nurse. Problem is somewhere else. Problem is maybe that vaccination itself. 10% of the people will complain. Problem is in the maybe the patient themselves. But by proportion, like 10% of the people will have this pain. But we should not blame nurse for that. So nurse are not the root cause, is null, and nurse are the root cause is the alternative. Another way of putting this is, I can say, proportion of mistakes or complaints or pain by nurse A is equal to proportion by B. And what is the suspicion? I think nurse proportion of mistakes, errors, delays, defects, here in this case, the pain complaints in nurse A is less than nurse B. That is what I am trying to prove. And looking at this data, I can say the p-value will be what, high or low? Can you tell me, looking at this data, what will be the p-value? In fact, I may say that it is actually p-value will be how much? I can predict the p-value also. P-value will be high, yes. Let me see. 10 divided by 100 can be 1. Actually, it is 1 only. Yes, you're right. See, you have started predicting the p-value also. Okay. It is 1. You will be 100% wrong. You will be 100% wrong if you say nurse is affecting, nurse is the root cause. Okay. You will be 100% wrong if you say. So don't say like that. So p-value is 1 proportion. And then again, this was 2 p-tests. I can even do chi-square. We'll see chi-square a little later. But let me talk about 1p tests. So let us say for COVID, let's say I'm a vaccine manufacturer, and my research team did some nice research, and we came out with there's a COVID Delta plus some vaccine which I have devised. I have developed. My team, research and development team, has developed, and I call it as Deltaxin. Deltaxin. Delta plus, whatever, Deltaxin plus. Now government tells me that government will approve the vaccine only and only if at least the efficacy is 80% on the population, because experts tell me that experts have told the government that if the vaccine is above 80%, if the vaccine is above 80%, the efficacy is 80%, means above 80% of the times it is able to develop the antibodies in the people, then automatically the community will develop the herd immunity, and it will get eradicated. That pandemic will be controlled. So at least for the population, it should be 80%. Okay. For 20%, it won't be effective, but it doesn't matter. But even if it is 80% for the population is taken care of, they develop antibodies, the pandemic will be gone. So I've developed one vaccine and I tested it on 100 people. And after testing on 100 people, I found 85 people got the antibodies developed within themselves. And I'm so happy. I say, wow, my efficacy is 85%. I'm very happy. And I submit to the government, but government listens to the black belt. Government listens to the the statisticians. The statistician does a 1P test. So null hypothesis is my proportion effectiveness is equal to 0.80, and alternative is what I am trying to prove, what I am here to prove. I am above 80%, because government says you should be above 80%, clearly. Even 80 is not enough, it should be clearly above 80%. So here I go for my 1P test, and 1P test tells me, okay, let me do the 1P test. I'm going to do the 1P test. 1P test, 1P test. One proportion test. How many events? 85. 85 people got the antibodies developed from my vaccine. And of course, I'm above. I've started dreaming of becoming a billionaire also now. I've told my friends, yeah, my days are now going to change. No more green belt, black belt training. I'll just relax on a beach, nice, billions of dollars. Relax, that's it. Nothing doing. Very happy. Now, government, unfortunately, government listens to the. So now government tests the hypothesis. Is Mr. Amitabh's vaccine greater than 80%? The p-value is 0.129. Oh, p-value is high. Null must fly. Government says, I will make 12% mistake, 13%. I'll be wrong if I select your vaccine, Mr. Amitabh. I don't want to be 13%. I can't play with the lives of billions of people. At 13%, no way. Sorry. P is high. Null must fly. You are not above 80%, Mr. Amitabh. Please go back. Sorry. Now again I go back, my team, then we really work hard again. And we add some chemical component, some nicely researched component, tested properly. And now we submit to the government. And now we conduct a trial. Out of 100, 92 people developed. So here the p-value was how much? 0.12. Now 92 people developed antibodies. Now again, government does a 1P test. Okay, let us see 1P test. I think you can also do if you want. 1P test. 1P test, one proportion tests. Now it is 92. Let us see. Let us keep my fingers crossed. P-value is less than 0.05. Government says now I'll be only 0.001% wrong if I choose your vaccine, and government says yes. Now I'm 95% confident, Mr. Amitabh, because now your p-value is almost zero. You are null hypothesis rejected, and you are above 80% for sure. Then 95%, government says now you are above 80%. Yes. With 92 out of 100, you are above 80%. Now I approve your vaccine. And I become a billionaire. Like, this is all dreams anyway. So, but you understood the 1P, 2P, that's enough. Okay, so that was our 1P test and 2P tests.